Hello everyone, today I will present my research on the value of streptomycetes in soil bioremediation and processes. This topic is highly relevant as we are facing increasing challenges in environment protection and sustainable development. Introduction: The challenge of the soil pollution. First, let's look at the critical global issue: soil pollution. Soil is the foundation of the terrestrial ecosystems and agriculture. However, it's increasingly contaminated by pollutants such as heavy metals and organic chemicals, mainly due to industrial activities, improper waste disposal, and intensive farming. Traditional remediation methods have significant limitations. Physical contaminations excavation is very expensive and damages the ecosystem. Chemical washing can cause secondary pollution. Therefore, a better alternative is microbial bioremediation. This method uses naturally occurring microorganisms to degrade or transform pollutants directly in the soil. Is it sustainable, cost-effective, and environmentally friendly? Why streptomycetes key features? Among soil microorganisms, streptomycetes stand out for several reasons. First, they are ubiquitous and highly stress-tolerant, capable of surviving in extreme environments such as drought, high salinity, and heavy metal contamination. Second, they exhibit filamentous growth, forming a dense network that enhances contact with soil particles and pollutants. Third, they act as a lateral chemical factory, producing a wide range of extracellular enzymes and bioremedataions that help break down the complex pollutants. Finally, they function as ecological regulators, promoting plant growth and helping restore health. Restore soil health rather than just removing contaminants. Mechanism 1: Degradation of organic pollutants. So, how do streptomycetes degrade organic pollutants? They rely mainly on enzymatic process. Oxidation reactions break down hydrocarbons. Hydrolysis decomposes pesticides. Mineralization converts complex compounds into harmless inorganic substances. In addition, they produce biosurfactants, which act like neutral detergents. These compounds increase solubility of hydrophobic pollutants such as crude oil, making them easier for microorganisms to degrade. Interestingly, recent studies have shown that some streptomyces strains can even degrade bioplastics, opening new possibilities for plastic waste management. Mechanism 2. Detoxification of heavy metals. Unlike organic pollutants, heavy metals can't be degraded, so streptomyces use different strategies. First, through bioabsorption, their cell walls build metal ions like magnet. Second, they can perform intracranial intracellular sequestration, storing metals safely inside the cell. Third, they carry out redox transformation, converting matter into less toxic forms. Finally, through bioremediation, they transform metals into stable, insoluble compounds. Together, these mechanisms effectively immobilize heavy metals and prevent them from entering the food chain. Bioremediation, ecological regulators. The role of streptomyces goes far beyond pollution removal. First, they improve soil structure by forming networks that enhance soil aggregation and porosity. Second, they enhance nutrient cycling, releasing essential nutrients like nitrogen and phosphorus. Third, they suppress pathogens by producing antibiotics and bioactive compounds. Finally, they promote plant growth, improving plant resistance into environment stress. In short, they have rebuilt a balanced and resilient soil ecosystem. Practical application case studies. These benefits are not just theoretic, they are already applied to real-world scenarios. Streptomyces have been successfully used to remediate soil contaminated with petroleum hydrocarbons, pesticides, aromatic compounds, heavy metals. Moreover, they work even better in combination with other approaches. Microbial capsule enhance degradation efficiency. Bioremediation integrates plants and microbes for better results. They are also effective in restoring degraded land, especially in saline or alkaline conditions. Challenges and future prospects. Despite their great potential, several challenges remain. Field conditions are highly variable, making consistent performance difficult. Native microorganisms may outcompete introduced strains. Additionally, some strains grow slowly, limiting remediation speed. However, the future is promising. We can discover new strains for extreme environments. Using synthetic biology to enhance microbial capabilities, design engineered microbial communities, conduct more field controls to validate their effectiveness. In conclusion, streptomycetes are versatile and multifunctional microorganisms. They can handle both organic and inorganic pollutants. They can survive in harsh conditions, making their ideal for contaminated environments. More importantly, they are key ecological regulators. Thank you.